two applications of the ideas that we've sketched out in the first 4 lectures. So basically this is to synthesize some of the constructions and concepts of the last week in 2 separate situations. The first is I'd like to return to the problem of understanding the rational surfaces over function fields. So let me recall the basic setup. We're going to fix a smooth curve over C with function field K, and I want X to be smooth, projective, rational surface. So by rational, let me just remind you that this means that over the algebraic closure, the surface is birational to P2K. It doesn't mean that it's rational over the ground field. So there's something that I should have mentioned before about these. So that's the notion of a model. So a model for X and I leave it for you to check that what I'm going to say as a model is the same as what Professor Tinkle described as a model. It's really all the same. So a model for X, a model for X is a morphism. So it's a flat, proper morphism with the generic fiber equal to X. And we'll say that this is regular if X is non-singular. We can always achieve this by just resolving the singularities. So we resolve if necessary. So maybe let me make a remark about all this. So we saw that if X is such a surface, we always have a rational point. So we discussed this, I think, yesterday at the beginning of the lecture. So let me translate what this means on the level of the model. So on the model, a rational point, let's call it X, will correspond to a section. This is a section of this morphism. So whenever you have a rational point, well, by definition, it gives you a rational section over a dense open subset of B. And by the standard arguments, just close up the image, apply the valuative criterion, you get a section of this fibration. Conversely, if you have a section of the fibration, you'll get a rational point over here. For the rest of the lecture, I'm going to go back and forth between rational points and sections without explaining it. And so you should feel comfortable with this, or make yourself comfortable. So let me make one other remark. So let's take a concrete example, and then I can draw a lesson from this. So let's say we have the following cubic surface. So I'm thinking of this as being defined over K equals CT which is a function field of P1. So when I take the model, a possible model will look like this. I just clear denominators and use homogeneous coordinates S and T. So this is going to live inside of the product of P1 cross P3. And I can take it to have the following equation. There's many choices involved. I mean, I can take many different models, but here's one concrete example. So I basically just clear denominators and homogenize the various pieces. The danger of writing an equation is that you can be wrong. Now, I want to draw one important observation, which shouldn't be that hard to see, but it's important to keep this clear. This is a smooth cubic surface. I mean, it's really just some twisted version of the Fermat cubic surface. It's perfectly smooth. But many of the fibers here are singular. So for example, if I look at the fiber over the points 1, 1, 1 minus 1, etc., we get these are singular. And so whenever I take these models, you need to visualize that you'll have some good fibers, which are smooth, and some singular fibers. And you can see the singular fibers just by specializing the parameters at various places. So here's the definition. Let me just say, so Professor Kresh and I are sort of living in parallel universes right now. He defined this yesterday. I'm going to define it today. It's a non-trivial exercise to see that his definition and my definition actually have anything to do with each other. So here's a definition. X satisfies weak approximation. If for any collection of distinct points in B, either of the following hold. So here's version 1. So for any regular model, anyone, not just the one you picked, but for anyone. You can see that this is not a very useful description, but let me, if we're given elements, xj, so this is in the smooth locus of the corresponding fiber. Given arbitrary points, there exists a section with these prescribed values. So pictorially, so we have some smooth fibers, we have singular fibers. If I have a singular fiber, I don't pick a singularity of that fiber. That's a bad thing to do. So I want to produce a section that traces its way through here with prescribed reductions at each of the places. That is, with prescribed values over each of the points B1 through BR. Here's an alternate approach. So for some regular model, so given a positive integer n and Taylor series of sections, I guess I should translate this into Hartshorne, right? By this I mean sections defined over the completion of the various points. There exists a section S so that S is congruent to SI modulo Ti to the n plus 1, where Ti is a local coordinate. At Bi. Hope that you can read that. Yes, that should be a curly X. Thank you. So you give me n. So for any given Taylor series, you pick them, any n in any Taylor series. There exists a section with a prescribed Taylor series. So the picture here is I have my fibration. And I tell you, all right, the section needs to pass through this point with this tangency, pass through this point, but is determined up to order 3 here, have a pointwise condition here. I just need to somehow find a section that snakes its way through with the prescribed tangent conditions, second derivative conditions at each of the given points. So let me just emphasize that really all I'm using here is that B is smooth of dimension 1. I'm using the fact that each of the points downstairs has a local ring that's a discrete valuation ring. So for B equals spec C, essentially the same definition can be made. And so if you translate everything into that context, you'll see that it does actually agree with what Professor Kresh told us about yesterday.
I'm sorry, and surely also in the second way, you also say that the image of the closed point of B hat is in the smooth locus of the fiber.
Well, if you have a formal section, it has to be in the smooth locus automatically. That's why I'm choosing everything to be regular, so I don't have to worry about that. It's just an intersection number computation. I'm not going to do it, but it's not hard. Or the implicit function theorem. It's probably the exercise. Use the implicit function theorem to show that if you have a formal section here where x is regular, then it can't pass through any singularities. See what the section and the morphism do on the level. Differentiate them. It's not that difficult. I don't think I need to say. I don't want to say much more about this. So here's a key remark. So this is a birational property. Of x. So if x and y are smooth and birational over k, that is that I can find a birational map from x to y, which is defined over the ground field. Weak approximation holds for x if and only if weak approximation holds for y. So in particular, by our classification, we're reduced to the cases of Del Pezzo surfaces and conic bundles. That is, if I want to prove weak approximation for all surfaces, because it's a birational property, I really only need to establish it for these classes of surfaces. So that, that P2 blown up at 137 points, you don't need to worry about it if you can just do the Del Pezzo surfaces. So at least we have a bounded class of examples we need to check. At least the fibers are bounded. So the last thing I should say is that weak approximation holds for the following cases. Well, it definitely holds when x is rational over k. That is P2, P1 cross 1. Anything that's rational over k, we have weak approximation because it's a birational property. For conic bundles, remember that fibration trick I did yesterday where I proved to you that conic bundles always have a rational point by bootstrapping? First I proved that the base has a rational point. Then I look at the fiber, and I prove that the fiber has a rational point using the 10-length theorem. The same bootstrapping argument will prove that weak approximation holds. So it's a similar argument from yesterday. Now, for Del Pezzo surfaces, it's fine provided the degree of x is greater than or equal to 4. Quartic Del Pezzo surfaces, quintic Del Pezzo surfaces, in all these cases, the result is known. The open cases are x Del Pezzo of degree 1, 2, or 3, including cubic surfaces. So for cubic surfaces, weak approximation is actually an open problem. So let me talk in very general terms about what makes it tricky. Well, these singularities here, these singular fibers, Del Pezzo surfaces with rational double points, with canonical singularities, they cause a lot of problems in our analysis. The real challenge here is to deal with the singularities in the fibers. The singular fibers, all these funny Del Pezzo surfaces, like the Cayley-cubic that I introduced yesterday. Remember this example? WXY plus XYZ plus YZX plus one other term is equal to 0. That causes us a world of trouble, the singularities in that surface. So this is really what makes the problem difficult, and understanding the singularities better is probably the key ingredient to making any further progress. So to support the fact that the singularities are the real difficulty, let me state one general result about approximation. So the general result basically says that as long as everything is smooth, we're in good shape. So I state this mainly to focus attention on the issues that are still open. So, definition. So a point B in B is of good reduction if there exists a model with the corresponding fiber smooth. And otherwise, bad reduction. So there's a finite number of these. So in the example that we did, I'll leave it for you to decide which fibers are good and bad reduction. It's not hard to check just by using the standard criterion. Here's the theorem, which is joint with Professor Tinkle. So any rational surface satisfies weak approximation at places of good reduction. So let me just emphasize here, what that means is that if I choose the points B1 through BR to be smooth points, so what I mean by this is that the points that I specified up there should be of good reduction. Now, you might think from the way I've set up the lecture that the proof of this involves going through the classification. I've definitely structured the lectures in such a way to leave that impression, and that would be a false impression, because we use essentially none of the classification to prove this. One way to make this clear is to state the hypothesis under which it actually appears in print, which is that this is true for any rationally connected variety. So the argument here is not of a classification nature. It's a very general argument. It doesn't use that much detailed knowledge of the surfaces. And we really, of course, like to have an argument that doesn't require detailed knowledge of the surfaces that proves the general case. The bad reduction cases are open. But from all the analysis that we've done, it seems like the bad reduction cases do require detailed knowledge of the geometry of the singular fibers. So did you have a question? No. Yes?
When you say satisfied with the approximation places of good reduction, you mean if we just pick the eyes of good reduction?
Yeah, pick them. You have a list of bad reduction places, throw those out, and then pick your points from the remaining ones. So for cubic surfaces, you get the section over the whole base, because this process of closing up, it gives you a section everywhere. And the section knows enough not to go into the singularities by the exercise that I was suggesting just there. So it stays out of the singularities. Other questions? So one thing that I want to emphasize about this this statement is very clean in the function field case. But as far as I know, this is open for number fields. So for number fields, if you take data which are not obstructed by the Bauer group, and that, I think if you have data that can realize a section, it's not at all clear that you can, even if you assume that places are of good reduction, that you can find a section. So this is much harder in the number field context. So let me say a little bit about cubic surfaces. So, yes. Yes. No, I don't think Q is any easier than the general number field case. But it's not known for any number fields. It's certainly not known for cubic surfaces.
Is the result still difficult if you instead of the function field of the curve, you take another field which is local, like the Piatic?
If you take the maximal unramified extension of the Piatics, there's no general guarantee of the existence of a point, at least in arbitrary dimensions. For surfaces, it looks plausible that there might be points. So you're asking whether you can find a section passing through a given smooth point of the closed fiber. Let's see. I think that should be doable, but I'm not sure. It's in some sense it's a little bit orthogonal because weak approximation is really a global statement, and when you're analyzing it over a local field, there's some cognitive dissonance that I can't overcome in the middle of a lecture. So you really want a situation where you have lots of different points in which to do your approximation. So let me say a little bit about cubic surfaces, just to show you how the structure of the singularities plays an important role. I must have there's the eraser. So here's some sample results. And these are just in the context of cubic surfaces. The first sample result is, let's say that we have a model x over b. Let's say we're given a model where x is regular and the fibers are all singular Del Petzl surfaces. Well, let me say it like this. Are all cubic surfaces with canonical singularities. So then weak approximation holds. For the generic fiber. So this includes situations where you have, in some sense, a generic family of cubic surfaces. So this includes the square-free discriminant case. Which, it's a pretty natural hypothesis in number theory that it's much easier to do things in a generic case where the discriminant has no squares than in the special cases where you have primes dividing it to high multiplicity. So here's another example. Let's say we're given a model where the fibers are all cubic surfaces with A1 singularities. Except for this frustrating Cayley example, which causes a problem. It's sort of irritating. So this Cayley example, the one singular cubic surface I wrote out in detail, is a fly in the ointment. I think someone should be able to remove this unfortunate hypothesis. So then we get that weak approximation holds. I want to emphasize here that the total space X may be singular. We may have singularities in the fiber. So I hope this shows a general principle that, at least given what the technology that I know, and these are all joint work with Schinkel, in order to prove results about weak approximation at places of bad reduction, it's really intimately tied up with the details of the geometry of the fibers. And we actually do use some substantial classification results as applied to the degenerate fibers of the fibration. So I'm about to completely change direction. So maybe I should open the floor to questions before I'd like to talk about universal torsors. Oh, there's a question, yes.
Now, if you just have a few fibers that have A1 singularities, you don't know them?
So the way the machinery works, going from one fiber to 150 fibers is not a big deal. I mean, basically, the procedure is inductive in the sense that if I can approximate at the first 150 places, if I just take that as a black box, let's say that someone from on high tells you, I have approximation at 150 places. If the 151st place satisfies your hypothesis, then you can approximate at all 151 places. It's an inductive process. So the number of places is not really the crucial issue. Another question.
Do you know cases where weak approximation does not hold?
Not for rationally connected varieties over function fields of curves. I mean, there are lots of varieties where it doesn't hold, but not for varieties that have some good negativity in the canonical class. I'm sorry? These are the ones that are of the topological type, C squared. These are resolved by one exceptional curve, square minus 2, and this is the type. Any other questions? All right. So time to move on to universal torsors. I was going to talk a lot about them, but Professor Kresch used them to great effect already. So I'm only going to dwell on a very small part of the theory, which is how to actually write them down explicitly. So explicit equations. For universal torsors. So let's let X be a rational surface. Oh, I'm working now over an algebraically closed field. I'm not going to talk about the descent issues, which are interesting but outside of my purview. We have a rational surface with, so the Picard group is equal to the Nerone-Severi group, and let's choose a basis. So this is a Z basis. We also have the Nerone-Severi torus, which is defined as so it's a torus of rank equal to the number of generators of the Picard group. And recall that we have the universal torsor which is defined as follows. If I let Li star be Li minus the zero section, so this is a GM bundle, a GM principal bundle over X. The universal torsor is just defined as the product over X of all of these bundles. So this is a GM R bundle over X. So what I'd like to do now is to, so this is, of course, a perfectly reasonable definition. But from Professor Kress's lectures, I think it's clear that we really want some way of generating explicit equations for this. So our goal is to try to write this down explicitly. And what that means practically is we want to represent U explicitly as an open subset of a nice affine variety. A nice affine variety that's naturally associated. I'm sorry? Affine. X is projective. So I should give maybe I should give an archetypal example to illustrate what's going on. I think that's the best answer to Damiano's question. So let me show you how to do this for P2 at the risk of boring people. So for P2, so let's take L1 to be, well, there's just one element, so it's OP2 minus 1. And let me just remind you that this is a universal subbundle. What I mean by that is if I think of L, I can think of L as being the following. I want to realize it in the product of P2 and A3, just consisting of pairs L, x0, x1, x2, where L is a line, and x0, x1, x2 is contained in L. And so the bundle structure is its projection onto the first factor. Now, inside of, so this is its projection onto the first factor. Inside of here, I have L star. And the key difference between L star and L is that I don't allow these points to go to the origin. So this is going to be the same, except that x0, x1, x2 is not equal to the 0. So here's a point. I can take this. So this is the universal torsor. can look at this under the second projection into A3. And so this is just equal to A3 minus the origin. So this is the identification I want. These are actually isomorphic to each other. So A3 minus the origin is a universal torsor over P2. And it is a dense open subset of an affine variety in a natural way. This is an archetypal example. We'd like to do this in as many situations as possible. So the key tool to make this natural is the Cox ring. So let me talk briefly about that. So I'm going to maintain those assumptions about X that I made over there. So we define the Cox ring. I just take a direct sum over all integers of the global sections of powers of these line bundles. So I want to think of this as a ring which is graded with respect to the Picard group. See, I can think of this as being a direct sum over all L of global sections in L. I multiply these in a natural way. If I have a section S in one line bundle and T in another line bundle, the product S times T is just here. So by virtue of this grading, we also get a natural action. I shouldn't say natural because it's not natural. We get an action of the Néron-Severi torus T of X on the Cox ring. So I just let the torus act on this graded piece by the corresponding character, which are indexed by the Néron-Severi group. Okay, so this is the basic definition. Let me state some important properties. So the first property is that the non-zero graded pieces of the Cox ring, these are in one-to-one correspondence to effective divisors. So, I mean, a piece is non-zero if and only if the corresponding divisor is effective. So this is the first hint that there's going to be some connection between the birational geometry that we spent a lot of time talking about earlier this week in the structure of these rings. The second property is that so the Cox ring, if it's finitely generated, this implies that the cone of effective curves, we write it in cone notation, is finite rational polyhedral. So this is an immediate consequence. So you're going to have a picture like this, that the cone of curves is a polyhedron. So in particular, you don't want to take x equal to the blow up you don't want to take this. This is a bad case, right? We saw that this effective cone is completely disgusting. Remember that was the one that had the infinite number of -1 curves lying everywhere? So this is not, you cannot have this and still have the finite generation. So this is bad news. But there's some good news. The good news is that if x is del Pezzo, well, let's think about this. We know that if x is del Pezzo, then from our discussion of the cone theorem, we know that this is finitely generated. And in light of the previous thing, it's natural to ask whether anything else, whether this implication factors through the stronger implication that the Cox ring is finitely generated. And it does. So this implies that Cox X is finitely generated. And that in turn implies that it's finite, polyhedral. Yeah, I'm playing fast and loose with the ones because I have a surface. Although this implication that the Cox ring being finitely generated, it does actually imply that this is finite polyhedral. But this implication in general is a theorem of Kiel and Hu in arbitrary dimensions. So that's actually a general theorem. It also implies that n upper 1 is finitely generated. So the last thing I should mention about the Cox ring, and this is really the $1 million property, otherwise we wouldn't care. I was going to prove this, but I don't think I have time, because I want to actually write down some equations. Is that there exists a Tx equivariant. Oh, let's assume that the Cox ring is finitely generated. Then there exists a Tx equivariant embedding, open embedding. Of U into the affine variety built on the Cox ring. Okay? Let's step back a little bit, come back to this example. What is the Cox ring of P2? Well, this is a direct sum. Right? And this is just, each set of these global sections is this polynomial of degree n. So this is just the polynomial ring. which is nice because the equivariant embedding I was referring to is right here. This embedding of U into affine 3 space with coordinates x0, x1, and x2. So this is really the archetypal example. And essentially, the property that the Cox ring is finitely generated is exactly what one needs to generalize this. So what I want to do for the rest of the lecture, well, for 2 minutes, I should do one other bit of explanation. So this formalism is useful for lots of things. You've already seen in Professor Kress's lecture how it's useful in applying descent and analyzing Riemannian obstructions. It's also very useful in counting rational points. So there's a good dialectic where when someone wants to count a rational point, they'll ask, well, what's the universal torsor equations? It'd be nice actually to have a computer program that would just spit them out. So in practice, though, we have a bunch of theorems that tell us what the answer are in many special cases of interest. I'm going to talk about these theorems. So they're due to a number of people: Skorobogatov, Cox himself, Batirov, Popov, and Darental. There are other contributions as well. I'd like to give some concrete examples where you can actually compute this. So let's come back here. All right, examples. So the first case is, let's say that X is toric. Then Cox X is isomorphic to a polynomial ring. This is a result of Cox, which is why I at least attach his name to this. Not everyone calls this a Cox ring. Some people just call it the universal coordinate ring, or I mean, there's other terminology for it, but I've never asked him. That would only put him in an awkward situation, so I probably won't ask him. But so this is a foundational result. And having this is one reason why toric varieties, why you can analyze their rational points, count them very nicely, is that you have a very explicit realization of the universal torsor as a dense open subset of affine n space. And that's very useful for many applications. So this includes del Pezzos of degree greater than 6. So the next relevant case is del Pezzos of degree 5. So here's the structure here. So let me first make a remark. So this cone, the cone of effective curves, is the cone generated by the lines on the del Pezzo surface. Remember, all the -1 curves are extremal elements in the del Pezzo surface. And in fact, so we know that these are extremal. And one can show, if you want using a computer computation, there are cleverer ways to do it, that these are actually the generator of the cone. And remember, this cone determines which graded pieces of the ring are non-zero. So in particular, we have some distinguished sections. So let's take a non-zero section in each of these. And so we get a surjective homomorphism. I'm sorry. We get a homomorphism from here to the Cox string. So the theorem is that this is surjective, and we can describe the relations explicitly. So it's exactly the quotient subject to the relations where these are the Pluker relations. For the Grassmannian. So what we get is that U embeds in the cone over the Grassmannian, which is an affine variety, as a dense open subset. So maybe I should say something about where these relations come from. So I'm not going to prove this, but I'm going to give you some indication of where. So I blow up I realize X is a blow up of P2 at 4 points in general position. So I let E1 5 equal E1. I use this notation for the 4 exceptional divisors. And I use this notation for the proper transforms of the lines through pairs of the points. So I get 10 of these all together. Now, the point is that I can write, say, L minus E1 in a number of different ways. This is L minus E1 minus E2 plus E2. L minus E1 minus E3 plus E3 So another way of saying this is that I have a conic bundle structure given by L minus E1 with fibers. Well, this is, I guess I denoted this by E12. This was E25. I get singular fibers that are unions of these exceptional divisors. So what this implies is that we get a dependence relation I get C1 X12 X25 plus C3 X13 X35 plus C4 X14 X45 equals 0 in the Cox string. I'm just using the fact that these three fibers are linearly dependent. So this comes from the fact that the dimension of O of F is just equal to 2. So if I produce 3 divisors in a two-dimensional vector space, there has to be a linear dependence relation between them. The trick is to see that it can be normalized to look like the Pluker coordinates. Yes? F is a class of the fiber L minus E1. It's a conic bundle fibration. So let me end with the description of a Cox ring of a general de Petzel surface. Let me, since I'm running low on time, let me assume that the degree